Okay, good morning, everyone. Today, let's wrap up chapter 6. There's a few slides remaining. We talk about RLC circuits, basically a second order filter. And then we'll talk a little bit about Bode plots, the charts that we use to describe filter responses. So let's go over to our notebook. Can everybody see the notebook online? Okay. All right, so the first circuit we're going to look at is the series resonance circuit. Now, resonance is a phenomenon that occurs in nature. We have mechanical resonance, right? You've heard of stories where due to wind or mechanical vibrations, a structure was destroyed or damaged. That is due to mechanical resonance. In electrical engineering, we also have electrical resonance. And the phenomenon that occurs is due to the energy storage capabilities of an inductor and a capacitor. Okay. And what happens at resonant frequencies is that sometimes voltages and currents that are larger than the source voltage may appear in the circuit. That is one of the results that could happen. And we'll see why that would happen. Okay. So here we have a series RLC circuit. We have an inductor, resistor, and capacitor, hence a RLC circuit. And it is an example of a second order filter. Okay, second order circuit. So since it is series, again, we are simply taking the output here. So there is no component connected across the resistor. So the circuit actually simply looks like this. We have an inductor, we have a resistor, and we have a capacitor. Okay. We won't do any circuit analysis on this, but we will go over the concepts and the equations. Okay. So this is Vs or Vin, source voltage. This is the inductor, resistor, and capacitor. Okay. Now, inductors and capacitors are duals of each other. They're very similar in property as well as exact opposite in many cases, right? The opposite refers to the phase or the phase angles of the capacitors and inductors. Now, I always talk about how these are energy storage devices, right? So if you apply a constant DC voltage that flows in one direction, the energy flows into the component. And when the source is reversed or removed from the circuit, then the energy flows back out of these devices back into the circuit. Well, when you apply an AC voltage or current to an inductor and capacitor, in one half cycle, electrons are moving in one direction, they're moving forward. So in the positive half cycle, the energy would flow into the inductor, and in the negative half cycle, it would flow out. Okay. Excuse me. And this happens constantly, right? Because the AC voltage or current is constantly bouncing between a positive and a negative peak. So in a positive half cycle, the energy flows in, the negative half cycle, it flows out. Capacitor is exactly the opposite. It is similar to the inductor, meaning it can receive the energy and send the energy back out. But it's the opposite of an inductor because the current leads the voltage. The capacitor will actually receive the energy in the negative half cycle and send it back out in the positive half cycle. So it's the exact opposite of the inductor. Okay. So if you have both energy storage components in the same circuit, the energy would flow out of the inductor and go into the capacitor. And in the next half cycle, it will flow out of the capacitor and go back into the inductor. Okay. So the energy keeps bouncing back and forth between the two components. And that's the basic gist of it. Now, of course, the quantitative analysis is far more complicated than we can get into a simple lecture class, right? But that's the gist of it. It is also one of the concepts that you would need to understand a reactive or complex power, which would be the next chapter next week. Okay. So you have an inductor and capacitor in the same circuit, and you apply a voltage or a current to that circuit. In the positive half cycle, the energy would flow into the inductor. In the negative half cycle, the inductor sends the energy out and then it goes into the capacitor, and then it bounces back and forth between the two, kind of like a tennis ball or a ping pong table. Okay. And that is one of the reasons why you can see a voltage or current that is larger than the source could appear in the circuit, right? If you have energy that is stored inside the inductor and capacitor, depending on the circuit configuration, that stored energy summed up along with the source would contribute to a larger voltage or current. Does that make sense? Right? If the energy is not balanced out between the inductor and capacitor, it could add up along with the source, and it could present along the resistance or any point in the circuit to a larger voltage or current. It is the source voltage. Let's say source voltage is 10, and the stored energy is like 5. Then the combined voltage due to the stored energy and the applied voltage would be 10 plus 5. And so higher voltage could appear in the circuit. Does not always happen, but it depends on the circuit configuration. Okay. What we are interested in is to see how the second order circuit could work as a filter. Okay. So at resonance, what happens? There is this phenomenon that occurs at resonance. It has to do with the impedance of the inductor and the capacitor. ZL is J2 pi FL. ZC is 1 over J2 pi FC. If they are connected in series, then the equivalent impedance of the inductor and the capacitor would simply be ZL plus ZC. Now, it's a simple derivation and calculation, but I'm not going to show that. If you add up these two terms together, and you set F, the incoming frequency, at a particular frequency, if you equate those two together, the impedances of the capacitor and the inductor in series would come out to be 0. And the reason is the magnitudes would be exactly the same, but the phase angles would be opposite. So if I was to draw a phasor diagram, let's say the impedance of an inductor started at and goes up to here. If this was ZL and you added ZC to it, ZC would start at this point and then return back to 0. Make sense? ZL plus ZC is exactly equal to 0. The magnitudes are the same, but the phase angles being 180 degrees out of phase would make them polar opposites, so to speak. And at that particular frequency, the impedances cancel each other out. The effective impedance of both in series would be equal to 0. And so the only thing left in the circuit would be R. The total equivalent circuit or total equivalent impedance would be equal to the resistor R. And because it's a series circuit, this ZEQ is labeled as ZS, series impedance. It's purely resistive at that point, meaning the output that you would obtain across that resistor would be at a maximum. Okay, output at that frequency, V out at F0 would be maximum. And that particular frequency, F0, is labeled or noted as the resonant frequency. Resonant frequency. If you plotted the transfer function of the circuit, it would look like this. we'd have the input frequency on the x-axis, transfer function h of f on the y-axis. We are taking the output across the resistor, hence the magnitude of the voltage, VR, divided by the magnitude of the source, Vs. Okay. F0 would be here, and that's your maximum. F0, and this is max. So maximum voltage would occur at the resonant frequency F0. For all other input frequencies, the voltage would be less than the max. Okay, on either side. If you increase the frequency, it'll start decreasing in this direction. If you decrease the frequency from F0, it'll start decreasing on the left-hand side. And hence, this circuit works as a band pass filter. It works as a band pass filter. That resonant frequency, F0, is a constant. It depends, well, constant as in fixed for a particular circuit. So it depends on the value of the capacitor and the inductor. So F0 is 1 over 2 pi root of LC. Okay, 1 over 2 pi root of LC. In the same terms, I can describe omega 0 as 1 over root of LC. Omega is 2 pi f, so if you take 2 pi on the other side, you get 2 pi f0, so it's 1 over root of LC. Always keep that in mind, especially if you're going to work with other engineers, they could be using omega 0. So I'll point that out every time. Any questions? Yes. That's just normalized. It's a normalized ratio. Yeah. Are you taking, you've done the lab, right? 251. Yeah. So in 251, the plots that we are plotting, they are not normal. They are not transfer function versus frequency. We plot V out versus frequency. So graphs and charts, you can take the data and you can decide what you wish to use according to your application. So this is kind of standard, plotting the transfer function, like a normalized transfer function. It makes it easier to compare. Yeah. Okay, so the next is FH and FL. If we take the max and divide it by √2, the intersection points give us two frequencies, right? One on the right, one on the left. FL and FH. The L and H just stands for low and high. It could be F1 and F2. It could be F2 and F1. Doesn't matter. In this particular illustration, in this book, they use FL and FH, so we'll stick with that. Basically, that describes the bandwidth of the filter. Remember, an ideal filter would have a characteristic that looks like this, right? An ideal filter would have a rectangle, meaning there's a certain band of frequencies which are allowed to pass. Everything else is blocked. Okay. Everything else is blocked. So in real life filters, again, remember 70%. These are the frequencies where the power drops to 50%. This is a graph of voltage versus frequency. If we plotted the power versus the frequency, and you can obviously do that with any data that you collect. If you plot power, P out, versus the frequency, input frequency, you would get the exact same frequencies at 50% of P out. Okay, 50% of the power translates to 70% of the voltage. So the point where the power drops to 50% at the output, equates to 70% of the voltage. And so that gives us two intersection. That gives us the bandwidth. And as with the other four filters we looked at, beyond these bands or beyond this band, you still have output, but we do not consider that as pass. We consider that as block. That's just a distinction engineers make. Okay. And this is, of course, just a second order filter because you have two energy storage components. There are higher order filters that will try to get this band or this frequency response as close as possible to the ideal with higher order filters. Okay, higher order filters. And then there are some other equations where we describe the quality of this circuit. Because it's series, the notation subscript is S. So Q is the quality of the filter or quality of the circuit to work as a filter. Okay. It's not the quality of the inductor or the quality of the capacitor. It is the quality of the circuit that describes its functioning as a filter. In terms of the components, you can describe it using both L, C, and R. In terms of the bandwidth, you can describe it using the ratio of resonant frequency to the bandwidth. Obviously, the narrower the band, the higher the quality, right? The wider the band, the lower the quality. So hence F0 over B, bandwidth. Make sense? Any questions? So let's look at a separate qualitative description. If I remove the capacitor and I still take the output across the resistor, if the capacitor is not part of the circuit, well, actually, let's work with the inductor first. So if I remove the inductor and I'm taking the output across the resistor, what kind of filter do I have? We only have a resistor and a capacitor in the circuit. Inductor is not present anymore. Output across the resistor. It will be high pass. It's two only options, but still, yeah. So we have a high pass filter, right? If the inductor is not present, then it's a high pass filter. If the capacitor is not present, what kind of filter would we have? Which taking the output still across the resistor. So, no, this is output across the inductor. Here. Capacitor is not present anymore. We're taking the output across the resistor. What do we get? Low pass filter. And then, as I was stating, if the inductor is not present, and we just have a RC circuit output across the resistor, we have a low pass filter, high pass filter. So we have both filters in here. Both filters in here. Does that make sense? So if I take and plot the characteristic of just the RC, what do I get? I first have, not first, but I'd have low pass filter, sorry, a high pass filter, and a low pass filter. So this is the high pass filter characteristic. This is the low pass filter characteristic. You have two cutoff frequencies, one for each kind of filter, the high pass as well as the low pass. You're bringing both of them together, and you bring both of them together, you get a band pass filter. Make sense? So the left side of the curve is actually a high pass filter because it is blocking all the frequencies lower than its cutoff frequency. And the low pass filter is actually allowing all the low frequencies to pass through, and it is blocking all of the frequencies that are higher than its cutoff frequency. And there's a narrow band or a small band between that are allowed to pass by both cutoff frequencies. Hence, it works as a band pass filter. Now, if you had your FL and FH here, You have a band of frequencies in the middle that's allowed to pass through. What if you switch the location of both of these filters? What do you get? If you take these two FL and FH cutoff frequencies, you switch the locations. They would intersect somewhere like this. You get a band reject filter. Band reject. So a certain band of frequencies, depending on the location of your cutoff frequencies, you would get a band reject or a band stop filter. BRF, band stop filter, BSF. It'd be a narrow band of frequencies that would be rejected. Everything else is allowed to pass through. This is particularly useful when we are trying to eliminate the signal noise from our power outlets. So power outlet signal is 60 Hertz. Sometimes it can cause interference. And so we use something known as a notch or a line filter. It filters out that particular signal frequency of like 60 Hertz. Okay, it's very, very narrow. It's a band stop, band reject filter. This also is a crossover network. It is a crossover network. If you take the output across the resistor, it is a band pass filter. If you take the output across a capacitor, it is a low pass filter. If you take the output across the inductor, it is a high pass filter. Okay. It's the same filter that does the exact same thing. And that's how you can actually take a single cable going into your speaker and split it up into 3 different parts. Okay. You've seen those 3 controls, right? Bass, treble, and mid. The mid is basically the band pass filter. This would be for the bass, and this would be for the treble. So crossover network comprises of inductors, capacitors, and resistors. At least the good ones. The cheaper ones would simply use like capacitors and resistors. Okay. All right, let's take a 10-second pause. Let me know if you have any questions. Does it make sense? Right? You have 2 filters, 2 first order filters in the same circuit, and hence it works as a band pass filter. All right, any questions? All right, then let's look at parallel resonance. Concept's the same, everything is still the same, just the analysis works a little bit differently. The cumulative effect of the capacitor and inductor in parallel is still the same. At resonance, impedance of the capacitor and inductor are exactly equal in magnitude, but opposite in phase. And this time, because they are connected in parallel, ZLC is the reciprocal of the sum of the reciprocals, 1 over ZL plus 1 over ZC. This gives you, what does it give? ZC plus ZL divided by ZL times ZC. So this simply becomes ZL times ZC divided by the sum. And we already established previously that ZL plus ZC at resonance would go to 0. So this becomes divided by 0, which means ZLC goes to infinity or behaves like a open circuit. Oh, that's one thing I missed previously. In series resonance, because ZL plus ZC goes to 0, it behaves like a short circuit, SC. Okay, it behaves like a short circuit in series. And in a parallel resonance, the combined effect of the impedance of the capacitors and inductors behaves like an open circuit because it tends towards infinity. So once again, any current that is coming from the source would not be going down the inductor or the capacitor because it may as well not be connected or part of the circuit. If it's open circuit, is an infinite impedance, it's not going to draw any current. Okay, everything goes down the resistor, and again, at resonance, V out is max. Okay, because the inductor and the capacitor do not draw any current whatsoever. And the equations we have and the chart that we obtain from plotting those is exactly the same as the previous one. Parallel resonance circuits are not as narrow as the series ones. They are quite broad. Okay. The equation for F0 is still the same. It's 1 over 2 pi root of LC. And then QP is simply the reverse or the reciprocals of QS, okay, in terms of the components. It's still the resonant ratio of the resonant frequency F0 to the bandwidth, but in terms of the components, it's still the same. Let's make it bigger. Okay, questions? It's still a second order circuit. The energy is still bouncing between the inductor and the capacitor. But after it receives the initial energy, it does not draw any more power from the circuit. Okay, the energy between the inductor and capacitor keeps being transferred between the two. And it's a concept we'll see again next week for reactive power. Okay, when you have a capacitor and inductor in the same circuit, the energy bounces between the two of them for an AC applied input. All right, any questions? Okay. So then let's look at Bode plots. H.W. Bode, that's who the plots were named after. The initial problem was to actually plot a very large range of frequencies on a very small plot, right? So if you think about the just the human hearing range, we'd go from tens of hertz all the way to like kilohertz, right? So if you try to plot that on a linear chart, it would be nearly impossible. You need like paper or, demonstration that is like about a mile long. So the problem was to plot very small frequencies and very large frequency ranges. And then, of course, very small magnitudes to very large magnitudes. Okay. So that was one of the challenges in trying to describe the functions of filters. So what it actually is, it's a plot of the magnitude of the transfer function in a special unit called as decibels versus the frequency. And that frequency on the x-axis is on the log scale. Okay. It's not linear, it's log. And so what it is, it's a straight line approximation using some asymptotes. So when we go to the log scale, we count the number of decades. Okay, we count the number of decades. Decades is basically the ratio of any two frequencies and the log of the ratio of any two frequencies. The base of that logarithm is 10. So if you take any two frequencies and you wish to find the number of decades between those, you take the ratio and take the log to the base 10. That gives you the number of decades between those frequencies. So for instance, 10 and 100, 10 and 100 as a ratio of 10. If you take the log of that ratio, you get 1 decade. Right? If you take the range 10 hertz to 1000 hertz, it's a ratio of what? 100. You take the log, you get 2 decades. Okay, so now we are squeezing a large range of frequencies into a smaller space by simply taking the log of those frequency numbers. Okay. It doesn't matter for this class, but I still wanted to like label it here. An octave is the ratio of two frequencies and the log of the ratio of two frequencies with the base 2. Okay, you would have heard how some singers have a large range, an octave. That's where that comes from. It's the log of the ratio of two frequencies to the base 2. Okay, so let's see how we actually use this for our plots. Anyone seen this kind of graph paper before? Seen, come across, used perhaps? Okay, so normal graph papers that we use, they are linear. They are linear. X-axis is linear, y-axis is linear, so it's linear. If both axes are on the log scale, we call it as a log chart. But a Bode plot uses a semi-log graph paper where only one of the axes is on the log scale, specifically the x-axis. Okay. Remember, x-axis always refers to the time or to the frequency, right? So for filters, we plot frequencies on the x-axis. So frequency f is plotted using the log scale. And since the y-axis is on the linear scale, it is known as a semi-log chart or a semi-log graph paper. Okay. The actual physical distance between each of these divisions is on the order of log of 2, log of 3, log of 4, and so on and so forth. There is no 0. Obviously, there is no 0 on the log scale. So the way you would use this would be using a multiplier. Okay, 10 raised to 1, 10 raised to 2, 10 raised to 3. So as an example, if I started with, let's say, 10 raised to 1 here, meaning my first marker would be 10 hertz. Second one would be 20, and then 30, 40, 50, 60, 70, 80, 90, and then it will go 10 raised to 2, which is 100. So I'm plotting 90 data points, if I wish to, 90 data points in a very small portion of my chart. Cumulative effect of the log scale allows me to plot very large frequencies. This would be 1 kilohertz. This would be 10K, 100K on 1 megahertz. I can go all the way from 10 hertz to 1 megahertz all in one small chart. And that is the beauty of using a log scale to plot my very large range of frequencies. Okay. On the y-axis, we have the magnitude of the transfer function, but that also is compressed. Okay. And this initially came about because there were some telephone engineers who were working on the power that was lost during transmission from one end to the other end. So they were trying to quantify the ratio, and what they discovered was the transmitted power at the input end was quite large and the received power was quite small. So trying to describe the ratio using linear terms was proving to be difficult. So they came up with a new unit The new unit was the ratio of the two powers. Okay, ratio of the two powers, P2 over P1. And they named it after Alexander Graham Bell, telephone engineers. They named it after Bell. So 1 uppercase B is the log of the ratio of the two powers. That becomes Bell's. To make that quantity even bigger, they came up with a unit prefix. If you remember from the first day of class, where I had the unit prefix table in chapter 1, deci, centi, milli, right? 1,000 millimeters is equal to 1 meter. 10 decimeters is equal to 1 meter. And so 10 decibels is equal to 1 bell. Or I can divide 1 bell into 10 different parts, or 10 decibels. And short form is dB, especially used in audio engineering. There are some high-end audio receivers that would actually give your volume output not on the linear scale, but they would give it in decibels in dB. Okay, so if you look at some high-end expensive audio video receivers on the market, on the front panel, when you change the volume, it would not be numbers going from 1 to 100, it would be dB. Okay, so 1 dB is 10 times log of P2 over P1. And it makes it easy for you to, for engineers to describe the gain in decibels, because, as an example, if P2 is twice the power of P1, or twice the value of P1, the gain in dB is just 3. It's just 3 decibels. And that is actually the amount that a human ear needs to increase or decrease to actually discern a difference in the levels. So if you have a 50-watt amplifier that's supplying 50 watts to a speaker, for us humans to be able to discern any change in the level, that minimum level is 3 dB, the power needs to double. It needs to go from 50 watts to 100. Okay, so the linear wattage does not mean much for audio engineers. That is also the reason why we use dB, especially for audio engineering. Okay, so this is the minimum level or approximate level at which humans can discern any change in hearing. Power has to be doubled for every 3 dB level difference. But when it comes to our filters, we are describing the transfer functions, which is the ratio of voltages. Since the unit dB concerns or includes power or relates to power, we change that to voltage by using the equation P equals V square over R. Okay, P equals V square over R. If you plug that into the equation for dB, then the decibel unit in volts comes out to be 20 volts. 20 log to the ratio of V2 to V1. Okay, 20 times log of V2 over V1. And so if we wish to describe the transfer function in dB, it is 20 times the log of H of F. H of F is the ratio of voltages. It's the ratio of output voltage to the input voltage, which fits this equation perfectly. And so if you wish to plot the magnitude of the transfer function, which has a very high range in filter circuits, right, on the x-axis, versus a large range of frequencies, we compress the frequency range by using the log scale on the x-axis. And then the y-axis is linear, but the data points, the values of the transfer function, are compressed by displaying them in dB or in decibels. And that equation is 20 log 10. The equation is 20 log to the base 10 of the magnitude of the transfer function h of f. Okay, let's take a pause. Let me know if you have any questions. Okay. All right, so Bode plots, you can plot both magnitude as well as phase. They are straight line approximations of the frequency response of a filter. Okay, they are straight line approximations. And these were particularly useful when we did not have computers to actually do our plots for us. Okay. Now we have computers and powerful software tools. Right before class began, we were discussing MATLAB as a powerful tool. And so MATLAB is another software that can be used for circuit analysis and for plotting, okay, for plots. And so manual plots like these, let's say this was the actual frequency response. This would be a manually plotted Bode plot. Okay, it would simply be a straight line approximation of the filter response. Okay, the slope of this filter response, whether it is a high pass filter or whether it is a low pass filter. This is a high pass. This is a low pass filter. The slope will always have a value of 20 decibels per decade of frequencies. Okay, so it's 20 dB per decade. And this is true for all first order filters. First order filters. As the order of the filters go higher, the slope gets, okay, we'll wait until you write it down. Okay, so as the order of the filters goes higher, remember I mentioned that it starts approximating an ideal filter. So the slope starts getting sharper and steeper. So a first order filter has a slope of 20 dB per decade. A second order filter would have a slope of 40 dB per decade, much sharper and steeper. Okay. Third order filter would be 60 decibels per decade or 60 dB per decade, whether it's going up or whether it's coming down. The slope remains the same. Okay. So again, these are straight line approximations of a filter response. All right, questions? Any questions at all? Yeah, does anyone have any questions about the problem, the example problem video on page 15? There are not a lot of views yet. Mm-hmm. Yeah. Sure. So the question being asked is, how did I get here? I simply plugged in the values of f. So h of f or h of 10 would be 1 over 1 plus j f over fb. This f in this case would be 10. So I would plug in 1 plus j 10 over, and fb is 100 for all, right? And so of course this then solves and becomes 1 plus j 0.1. And then we would solve that using our calculators, or the way I would do it is I would change the denominator because I'm performing a division, 1 divided by something. I would change, this is basically 1 angle 0, and the bottom would be some magnitude, and some phase. And then I would perform that division. Phasor as in from here to here? No, it's not a dumb question. So this is rectangular coordinates. This is just the coordinates. So this is polar coordinates. But students should be able to simply plug this in their calculators and be able to obtain the final value, which is 0.9950 minus 5.71. This equation right there. 1 divided by 1 plus j.1. So what the students would do is they would program this equation. And again, I wouldn't know how to do that because every calculator is different. I don't have one of the programmable ones, so I've never used those. So I do a manual calculation by converting the coordinates. So in this case, since I have rectangular coordinates in the denominator and I need to perform a division, I would ensure that both the numerator and the denominator are in polar coordinates. So 1 plus j.1 means it is a vector that has a magnitude of 1, or projection of 1 on the real axis and the 0.1 on the imaginary axis. So if I was to plot that, let's say 1 plus j.1, it would look something like this. This is obviously not to scale. So 1 would be here, and 0.1 would be somewhere here, right? And so the intersection of the 2 points gives me the polar coordinates. This would be the r, and this would be the phase angle theta. So I'd have magnitude r with a phase angle theta right here. Then I would perform the division, which would be 1 divided by magnitude r and the phase angle 0 minus theta. That would be the manual way to do this. But if students have a programmable calculator and you program that equation into your calculator, you would directly obtain the final answer. So students would simply program. Has anybody done it, by the way? Anyone in class or online? Have you done it? Do you get the same answer? Okay. Okay. All right. So thank you. So yeah, you can simply program the calculator and yeah. So if you don't mind, if students do not know, just show how to do it, like, within 5 or 6 minutes if you can. Okay. Any other questions? So that is the end of chapter 6. Bode plots at the end. There's a homework that was due tonight. I just shifted it. I think I shifted to like Saturday night, just to give students some extra time. So chapter 6, as I mentioned, will not be tested or assessed on the final, but I will assess it separately on the quiz on Monday, and I will post details later on. There are 3 homework assignments related to chapter 6. One was due tonight. I made it due tomorrow night on Saturday, and the third one is due on Sunday night. Okay, same time. Reach out to me if you have any questions. There are some example problems. 1 or 2 of those are exactly the same as the ones that I solved in class and the video solution that I posted. And then most of those are conceptual questions to ensure that students, work on their concepts. Other than that, there's nothing too difficult that I foresee about those homework or assignments. Okay, all right. I'll bid you all a good weekend, and I will see you all on Monday. If anyone has questions, I'm still around. I still have 10 minutes before the next class.